Hello everyone, and welcome back to another GIS lecture video. And in this GIS lecture video, I want to continue our discussion on the viewing geometry of satellites and GPS by talking about how we actually quantify the quality of that geometry, right? And you'll remember from the previous video, we had that diagram where we looked at how the arrangement of the satellites actually affected that sort of area of uncertainty. And as we pushed the satellites closer together, that area got larger, meaning that we had less accuracy. So how do we actually quantify that in a way that you're out in the field and you can sort of look and see and say, okay, this is a good geometry or a bad geometry? Because you obviously can't see the satellites, right? That's impossible. Well, what we've come up with is we've come up with this thing called dilution of precision. Dilution of precision. And there's actually several different versions of it, but the most commonly reported one is called positional. Right, positional dilution of precision. And if we take the first letter of each of those words, we get what's called P-dot. We get what's called P-dot. P-D-O-P. P-dot. And you'll see P-dot pop up all over the place in GPS. And whenever you see this acronym, it stands for Positional Dilution of Precision. And basically what P-dot is P-dot is a single numerical value that represents the quality of the viewing geometry of the satellites, right? So this is a numerical value or a number, right, that represents the quality of the viewing geometry. Right, it represents the quality of the viewing geometry. And as a general rule, right, as a general rule, the lower the better. The lower the better. So without going into too much detail in terms of how this thing's calculated, because it's fairly complicated mathematics, but basically what we're doing is we're comparing the shape of the viewing geometry that we actually have with what would be considered to be the ideal viewing geometry that would be possible. And the closer those two things are together, the lower the P-dot. The farther apart they are, right, the more the actual viewing geometry deviates from the ideal, right, the higher the P-dot gets. And so the range of values you will typically see for a P-dot ranges from, right, P-dot ranges, right, it ranges from 0 and then 20 plus. And the reason I put the 20 plus here is because you will see numbers higher, but typically 0 to 20 are the ranges that you're most likely to see. And again, lower is better. So the closer to 0 you are, the better off you are. And again, this is just a representation of the viewing geometry quality. So when you're out in the field and you're collecting data with a GPS unit, typically what you'll do is you'll do one of two things. You will either set the receiver up so that it has a P-dot filter, meaning that if the P-dot jumps above a certain threshold, it will stop collecting data. Or when you look at the GPS receiver, typically it will report out the P-dot somewhere on the screen where you're actually collecting the data. Right? This is a pretty important number to pay attention to. So the GPS units are pretty good about reporting it. So what you could do is you either set an automatic filter to just stop when the P-dot gets too high, and typically it'll warn you. Or you will look at it manually when you take the recordings and say, okay, well this P-dot was really high. Let's wait a minute, wait for the geometry to change a little bit. Maybe the viewing geometry of the satellites we have will change. Maybe we'll get an additional satellite will come into view that will change the geometry and lower the P-dot. But again, lower is typically better. So let's go ahead really quickly and talk about some sort of talk about some sort of ranges that you would typically likely see. So as I said, PDOP ranges from 0 to 20. Typically, sometimes you'll see more than 20, but 20 is about as high as you would hopefully ever see during a GPS mission. So if you ever manage to hit between 0 and 1, this is ideal. Right, this is great. This is what you should strive for. 1 to 5 is typically considered a good PDOP. So you might often try to set your thresholds and filters and stuff to threshold under 5. If you're really concerned about accuracy, because you're probably not going to get between 0 and 1 that often. You would have a hard time continually having this. 1 to 5 you can get pretty reasonably. If you're in a poor area where you have a lot of buildings or a lot of trees, or maybe you aren't as concerned about being really accurate, you could go from 5 to 10. Right, this is considered moderate. And then basically after 10, you really kind of want to be a little more careful with it, right? Because 10 to 20, we would consider this to be fair. And then 20 plus is considered poor. Right? And so when you're actually collecting data for most purposes, you really want to be in these first two categories. Basically between less than 5 is ideal. Again, if you're really desperate or you're in an area where these aren't possible, again, it could be buildings, it could be tree cover. You just don't have good geometry. Because again, the geometry here requires you to be able to see the satellites. And as we talked about in the video on error with multipath error, right? If you're in a very densely tree canopied area, the signals may just never reach the receiver, or at least they'll be of such poor quality that they wouldn't be counted. And that would raise your PDOP because you have fewer satellites. So ideally, you'd want less than 5. And hopefully this makes sense. Again, just to recap, right? Dilution of precision, or PDOP, is a numerical representation for that geometry that we talked about before, where the idea is that we want to have our satellites more spaced out on the horizon rather than clustered together. And the more spaced out they are, the lower this PDOP will be. The more satellites you have, the lower this PDOP will be. And the idea is that we want to have a value less than 5 when we're collecting data, because this is a good indication that our viewing geometry is going to give us a smaller area of uncertainty. And remember, we talked about that diagram where as we move the satellites closer together, right, the area that we were predicting in got larger because the ranges of the different satellites overlapped more, which meant that we were less certain of our specific position. So hopefully this made sense. And as always, if you have any questions, please reach out. Thank you.